Okay. Yeah. Good afternoon, everyone. I am Edi Tribaskoro, and it's a pleasure to welcome you all to the Combinatoric Today series. It's wonderful to see you, and also I recognize we have many familiar faces face here, and also new participant joining us for another exciting session. First and foremost, I want to express my deepest appreciation to your enthusiasm and commitment to this event. When we launched this series, 2021, our goal was to foster a vibrant academic environment that supports research and development in combinatorics and graph theory. Thanks to your dedication, we've made a remarkable progress together, and I couldn't be prouder of what we've built as a community. And I would like to extend my heartfelt gratitude to the Department of Mathematics and Faculty of Mathematics and Natural Sciences for their big support in making this series possible. And today we are honored to welcome a very special guest, Professor Sylwia Cichacz from AGH University, Cracow, Poland. And I think many of you are already familiar with her outstanding contribution to graph theory and combinatorics, particularly in graph theory and graph labeling and fault tolerance system. Her research has been a major inspiration for scholars in the field, and we are privileged to have her here with us today. And she will be delivering a fascinating talk titled Application of Zero-Sum Sets in Magic-type and Antimagic-type Graph Labeling. And this session will be chaired by Dr. Rinovia Simanjuntak. And before we begin, I'd like to take a moment to acknowledge the incredible organization that helped bring this event to life. First, the Combinatorial Mathematics Research Group, Institut Teknologi Bandung. And then second, the Indonesian Combinatorial Society. And third, the Center for Research Collaboration on Graph Theory and Combinatorics in Indonesia. All right, that's enough from me. Without further ado, let me pass things over to Dr. Rino. Dr. Rino is yours.
Okay, thank you, Pak Edi. I think before we start, let's take pictures first.
Okay.
Oke, Pak Edi bisa ambil fotonya ya, Pak?
Okay, yeah.
Okay.
Just give Ababa.
Okay, so please open your
Camera.
camera.
Yeah.
Wait a second. Okay. So I think it has to be several times ya, Pak Edi ya?
Yeah.
Okay, there are two. Okay, two screen, I think. Okay. First screen first. 1, 2, 3, smile.
Okay.
Second screen.
Yeah.
1, 2, 3.
All right.
Okay, thank you so much.
Yeah.
Okay, thank you. Okay, so it is my honor to be able to introduce our next speaker for the Combinatorial Mathematics today, which is organized by the Combinatorial Mathematics Research Group at ITB. As Pak Edi mentioned before, our speaker today is Professor Sylwia Cichacz. I always have difficulties of pronouncing your name. From AGH University in Cracow, Poland. I think Sylwia is already a collaborator for some of us in Indonesia. But unfortunately, Sylwia hasn't visited us in Indonesia, Sylwia. So probably next time you can come
Next time.
to visit us in
I will
Indonesia.
try to change it.
Must go to
Okay,
Bandung.
so I will give a short introduction of Sylwia.
Oh.
So can you see the slide?
Yeah.
Okay.
Yes.
So Sylwia Cichacz is an assistant professor at the Faculty of Applied Mathematics at AGH University in Cracow, Poland. She graduated from the same university, AGH University, with PhD in discrete mathematics in 2008. And she also started his academic career in AGH University, in 2003. And then she also visited the University of Minnesota Duluth in USA. I think she visited Professor Dalibor Froncek at the time in 2014. And also Sylwia did postdoctoral and visiting professor in Koper, Slovenia in 2012 and 2018. And she is now an assistant professor at AGH University since 2010. Sylwia research area is primarily in labelings of graphs and fault tolerance systems. And within this research area, she already published more than 70 research articles. And today, Sylwia will present a topic application of zero-sum sets in magic-type and anti-magic-type graph labeling. So without further delay, I will invite Sylwia to present her results. Please, Sylwia.
Okay. Thank you very much. I'm really honored and it's a great pleasure to give you this talk. I'm very happy to see all of you, my friends from Indonesia. So I will share my screen now. Okay, do you see my slides?
Yeah.
Okay,
Yes.
perfect. So this is the joint work with some of my collaborators. As you see, even you mentioned today with Dalibor Froncek from Duluth. So I will start with zero sum in graph labeling, but so the first will be introduction, and then I will tell you a little bit about zero sum sets, and then I will present you three application to graph theory. I mean, to three types of graph labeling. So I will start with some definition very simply. So gamma will be for me a finite abelian group, and zero is the identity element. And because this is abelian group, so I will use the operation is like gamma and plus. So 2a is like a plus a. The minus a is the inverse. A minus b is a plus inverse of b. So this is the standard notation. I just want to be sure that you will know what I'm talking about. And a subset S of elements of gamma is called zero-sum subsets if the sum of these elements under the operation in the group is the identity element. So for instance, here I have the direct product of Z2 times Z2. So this is an abelian group. And I have 1, 1, 0, 1, 1, 0 elements. And this is the zero sum subset of the elements of this group. And because I will be labeling graph, not only edges, but in that example, edges, okay? And I will be saying about like zero sums structures in the graph. So here now the blue labels, you see, they will sum up to the identity element, right? Because on each coordinate, once more, this is the group Z2 times Z2. So on each coordinate, I'm doing modulo 2 operation, right? So this is like 0, 0. So this is like 2, 2. In this, I'm taking modulo 2, and this I'm also taking modulo 2. So I will obtain 0, 0. So identity element, right? Okay. So the blue edges, they are zero sum subset. Okay, and there are like two ways to look to zero sum structures in graph in group theory. I would say not in graph but in group. So the first is connected with this guy, and probably you know who it is. This is Ramsey. So this is Ramsey type problems, and this is like very well studied, right, in graph theory. It's like how many elements. The problem is typed in such way: how many elements should a certain combinatorial structure have, such that certain special substructure appear, right? So we very well know this problem about the parties with 6 people, and there are 3 who knows each other or 3 who don't know each other, right? But there are a lot of many of variation of these problems, and one of this is this definition, which is connected. So I have that K divides the number of the edges in the graph G, okay, and the zero sum Ramsey number in the group cyclic group zk is the smallest integer r, such that for every zk coloring of the edges, so I'm putting the elements of the group zk on the edges of the complete graph kr, there is a zero sum copy of G in KR. So this is like connected to this Ramsey number, because here we are looking for a structure that has zero sum. And in that, with 6 people on the parties, we are looking for blue or red, right? And theorem, another thing connected with this is the theorem that started that problem, is that 2n minus 1 is the smallest integer, such every sequence over a cyclic group Zn has a zero sum subsequence of length n, right? This is, we can see that this theorem is similar to theorem of Cichacz about like monotonic sequence, right? And here is we are looking for zero subsequence of length n. And the question in that branch of zero sum sets came from Białostocki and Dicker in 1990, and the question was, what is the smallest number n, so that any complete graph Kn with edges labeled by the elements of finite group, look, here is not necessarily cyclic, but finite group, contains a subgraph of predescribed type with the total weight of the edges 0 in gamma. Okay, so this is one branch. I'm not working in that, so I'm not an expert in that particular topic. I just wanted to show you that there is one branch of zero sum subset in Abelian group. And this is connected with Ramsey number. So the definition is zero sum Ramsey number Rg gamma is the smallest integer r, such that for every gamma coloring of the edges of complete graph Kr, there is a zero sum copy of G in Kr. And this is the connection between the Ramsey number, like regular one, right? Because this is the order of the group, and this let's say gamma Ramsey number. And I will show you only 2 theorems. One is due to Alon and Caro, who proved that if n is sufficiently large as a function of k, then we have this upper bound, so the Ramsey number of Kn in Zk. So we are looking for zero sum copy of Kn in the clique, and the clique is to be at least of this size. And for non-cyclic group, I have these two results here. So one is the upper bound in the group Zn2 square. So this is the group I already considered, is that group. And we have the upper bound for forests. And here we have the exact number for a copy of the cycle C4. Okay, so this is one branch of zero-sum sets in abelian group connected with graph theory, and the second one is connected to that guy, and this is Steiner, right? And this is Steiner. So the Steiner type problem is, does a certain combinatorial structure have a decomposition into certain special substructures? And we know very well about the Steiner triple system in graphs, right? Which is named by his name, although he was not the first who was working on that, but the name is after him. And this is the way that I working on. I mean, on that type of the question. So it started in abelian group with triple systems, right? From this Steiner triple systems in cyclic groups. So in the groups Zn, in cyclic finite groups. And in 1957, Skolem, he asked, for n which is congruent to 1 mod 6, does there exist a partition of the set of non-zero elements of the cyclic group Zn into triples such that they are zero-sum? So note that this n congruent to 1 mod 6 is a necessary condition, right, for such partition. Why? One could think, why not 1 mod 3, right? 1 not mod 3. But then n could be also like 4 mod 6. So n is even. And if n is even, then your group has elements like 0, 1, okay? And then I have n divided by 2 and up to n minus 1. This is your group, right? And when you sum, let's say not without 0, all the remaining elements, so non-identity elements, then the sum is not 0, right? Why? Because this is the element that is inverse to itself. So you can join elements into pairs, like element and the inverse, elements and the inverse. And this one will be without a pair, right? So the sum in that set is n divided by 2. So the necessary condition is 1 mod 6, because then the group is of odd order, right? And the sum of non-identity elements I can join to these pairs, and the sum will be 0. So this is the necessary condition, okay? So here is an example, very easy, Z7, and we see that we have this decomposition of this group into 2 triples of zero sum. And the answer was yes. And Skolem gave it in 2 papers. And now I'm sorry, but I don't remember. But I guess that the first was 1 mod 24 in 1957, and the second was 7 mod 24 in 1956, and the remaining cases were solved by Hanani later. Okay, so the answer was yes. And then Tannenbaum, like 10 years later, after the question was posted, he generalized this question into any finite abelian groups. Okay, not only cyclic, any finite abelian groups. Okay, and what is the useful tool? And I will show you this definition, because later I will use it. So a 6 subset, so a subset with 6 elements of abelian group, we will call good if it has this property. So look, I have like these 3 first elements, they sum up to 0, you see, and the same is with the second one, right? Triple. Because I have like C plus D plus minus C minus D, right, which is 0. But it's not only this. Also, we have like pairs that they sum to 0. D minus D, C minus C, and this element sum to 0 to this element. So what is idea in that good SIG subset is that you can partition this subset into 2 triples that sum up to 0 or 3 pairs that sum up to 0, right? Okay. And Tannenbaum gave a definition that a finite abelian group of order M, which is odd, okay, I have this 6k plus s where s is some odd number, has a partition into k good six subset and s minus 1 divided by 2 zero sum, 2 subsets, is called a Skolem partition of gamma. Okay, so I will show you now, the example. So this is the Skolem partition of gamma. So 9 minus 1 is 6, which is 1 times 6 plus 2. So I want to find one good subset, which is this, right? And I have one pair which sum up to 0. Okay, so do you understand the concept? So let's say that if I have, I don't know, a group of order, let's say 15, then 15 minus 1, I subtract this 1 because 1 is for the identity element, will be 14, and 14 is 2 times 6 plus 2. So I want to find a partition of my group gamma into 2 6 good subsets and 1 0. Okay, so this is the definition of Tannenbaum and of the Skolem partition. Okay, and he proved that every finite abelian group of odd order has this Skolem partition. Actually, he proved he was working first on this Steiner triple system, and then based on that he proved that theorem. Okay, and the corollary of this theorem is, maybe it's not so easy to see at the beginning, but I will explain you why. That if I have a gamma, which is an abelian group of order n, which is odd, then for every partition of the number n minus 1 into t numbers, such that each number is at least 2, and this is for any possibility, there exists a partition of non-zero elements into pairwise disjoint sets A1 up to AT, such that the set AI has exactly Ri elements, and the sum of the elements in the set is 0. Okay, so this is the corollary, and now I will show you the core of this corollary. So I have this Z9, okay, and here are all possible partitions into 0 sets that they have at least 2 elements in each set. Okay, and one can see that it's not important if I have like this the partition to 2 0 sets like 1 8 2 7 and this 4 0 set. It doesn't matter what elements are in the set. I only care that I have a partition into some sets of that size. So it means that actually it's enough if you can partition your set, this set, into pairs and sets with 3 elements. Because if you have these thread partitions, then you can obtain everything which is below, right? Like you can obtain, let's say, this partition using that partition, right? Because I will join these 2 sets into 1. You can obtain, let's say, this partition using that partition, because I will take, right, 1 0 sum 3 sets, and then remaining sets I will join. But you can observe something more. Then actually this column partition, which is here, is enough for us, right? Because if I have this column partition, then I have these 2 red partitions. So from the Skolem partition follows the partition unmentioned. Okay, and now that was for odd groups, let's say odd, I mean the order of the group, everything is done. So what about the groups with even orders? And with even orders is a little bit more complicated. So first I need a definition of what is the involution. An involution is a non-identity element which is the inverse to itself. And by I of gamma, I will denote the set of all involutions in gamma. And there is this theorem that the sum of all elements in finite abelian group is either the identity element or the involution, if the set of involution has exactly one involution. Okay, this is quite easy to understand because I have like 0 and then I have one involution, right? And then I have disperse A minus A, B minus B, right? Because I have no element that is the inverse to itself. So if you sum all the elements in that group, right, you will get that only involution is without a pair. So that's why I have this sum. This is a little bit more difficult, and the proof is technical, so I don't want to show it. You have to believe me that it's some basic fact from abstract algebra. And what is important by let's say Lagrange theorem, if the number of evolution, if the order is even, then the number of evolution is at least 1. Okay, so if the group has even order, then has to be at least one involution in that group. This is also a fact. An example. So Z6, I have such elements, and I have one involution which is free here. Only this element is the inverse to itself. And when you sum all the elements in that group, you will get the sum will be free, right? Modulo 6. And another example is the group I mentioned today also. It's the Z2 times Z2. And now when you sum all elements in that group, right? Because you are taking modulo 2 on each coordinate, when you sum, you will get 0, 0, right? All of these elements are in the evolutions in my group, right? Because 1, 0, let's say, plus 1, 0 is 0, 0, right? In the group Z2 times Z2. Correct? Because it's like 2, 0, which is 0, 0. Okay, so this is some facts from the abstract algebra. And now some theorems. So Zeng, I will mention about him later also, because he needed that theorem for graph labeling, but I will tell you about this later. He proved that if we want to find a partition into pairwise disjoint sets such that each set is at least of size 2, right? Then this is possible if and only if, sorry, I shouldn't have this word, if and only if the number of involution is 0, so the group has odd order or is free, And it's not so difficult to see that this is a necessary condition, because suppose that the number of involution, okay, can be, the next number is 7. Is 7. And my group gamma is of even order, so gamma minus 1, so minus the identity element is odd. So suppose that this is like 2m minus 1. So what I want to do, I want to partition my set. Suppose that one R1 is free, and all the remaining R's are 2. And this is impossible. Why? Because I have 7 involutions, okay? So on 3 involution can jump to the set of size 3, but there are 4 that are left. So they have to be splitted in some set of size 2. And if you have an involution and some other element, the sum won't be 0 for sure. Okay? Doesn't matter what happens, what is A, the sum won't be 0, because you can have only the set of size 2 in abelian group that sums to 0 in the form the element and the inverse of the element, right? So it has to be that the number of involution is either 0 or 3. And it was conjectured by guys in graph theory, you know probably that name, Kaplan, Lev, and Rodity in 2009. And he proved it in 2016. And for some other groups, actually for one group, so this is Z2 to the power of M. If you think about that group, this is the group which only has involutions. They are like binary vectors, right? This group has like binary vectors. It's either on each coordinate is either 1 or 0, and the operation is taken on the coordinates modulo 2, right? So you have only the involutions and the identity elements. And the Tannenbaum and independently Egava, who works on graph theory, and independently Zaceta and Chia, who also works on graph theory, they prove that if you want to partition this group, sometimes it's called Boolean abelian group, into sets, such that each set, it has to have at least 3 elements for the reason I mentioned before, then it's possible always. Okay, of course, if M is at least 2, so the group is not cyclic. Okay, and Tannenbaum, he conjectured in 1981 that suppose that, let's take your group. This is the set I of G is the set of involution. And let's take all the elements which are not identity and not involution. So there are like pairs A minus AB minus B and so on. Then for every possible integer T and every partition such that we have like for every I, which is from 1 up to numbers of parts divided by 2, the set is at least 2, and the set is at least 3 for the involution. So the idea was, okay, I know that I cannot put the involution into sets of size 2, but maybe I have some sets of bigger order, and then I will put these involutions to that set, and probably this partition will be possible. Now that was conjecture, but the conjecture is false, which I proved with my colleague 1 year ago. And actually it holds only for the group with exactly 3 involutions. I have this assumption, or with the group of that size, and actually in that group we have the numbers of involutions like this. So the conjecture is false. And this is a partition why it's holds, but it's more technical, so I'm not going to the details. But if you want to see, this is the partition that fails in that conjecture. Okay, so what we were able to prove with my colleague, we were able first to prove that if we have a group of order 2 to the power of n with more than 1 involution, then every partition that every set is at least 3 is possible. And 1 year later, we don't have an assumption for n. Okay, so n is any number. So not in the form 2 to the power of n, but and the number of involution is also at least 1. But we were able only to prove that in the partition, each set has at least 4 elements. Okay, has at least 4 elements. I'm not saying about the proofs of these theorems because they are in abstract algebra and quite technical, and the background from abstract algebra is needed. I'm just showing you those theorems. But before that, and I will show you the sketch of that proof, with Zsolt Tuza, we are able to prove that if group gamma has big enough order, then we can find the partition. But the set has to be at least 4, and this result was improved this year by using similar methods to mine and Zsolt, that each set is at least 3. But the group also has to be big enough, whatever it means, like very, very big, right? This is the asymptotic result. Okay, so this is everything from the abstract algebra, but I will show you some open problems, and I will show you my conjecture, which is still open. So I believe that you can do this partition such that any set is at least of size 3. So we are very, very close, but we have either an asymptotic result or we have that n has to be large enough. Okay, So only that is proof. Okay, so now applications. I put here my magic square, which was made by my daughter. I would say it was for, maybe Rino and Kiki, they remember, it was made for Dalibor's 70th birthday. And I really like that magic square. So the application is about to magic and anti-magic types of labeling. So the magic type is simply saying that we are labeling some elements, right, of a graph, and we want to have that some other elements, they have the constant sum, right? I mean, you are summing edges or vertices, it depends on the labeling. And the anti-magic is like anti of this labeling. So we are labeling again something, and we want to have that something has pairwise distinct sums. Okay, and I will start with anti-magic labeling. So I will start with very old definition, so that the anti-magic labeling of a graph G is a bijection. So now I'll be speaking only about graph theory, so not about the abstract algebra. It's a bijection from the set of edges to the integers from 1 up to e, such that all vertex sums are pairwise distinct, where a vertex sum is the sum of the labels of all edges incident to that vertex. So suppose I have a star, right, and I'm labeling 1, 2, 3. So I have a bijection, and now this vertex get the label 1, this 2, and this 3, and that one will get the label 6. I'm doing that into the numbers, not modulo. So every sum is distinct. So this is the anti-magic labeling of a star K13, right? And there is very old conjecture that every connected graph other than K2 is anti-magic. And this conjecture is open even for trees, and there are a lot of people who try to solve this conjecture, but the conjecture is still unsolved. I'm showing you some theorems. So Alon, Kaplan, Lev, Roditi, and Euster, they prove that there exists a constant C such that if G is a graph with n vertices and minimum degree, which is this C, this constant C times log n at least, then G is anti-magic. And it was somehow improved by Eccles in 2016. So he proved that there exists D0 such that if the average degree is at least this D0, then G is also anti-magic. But you see, the problem is quite difficult to solve. It's still unsolved. And there are, like I said, a lot of people working on that. There are different approaches to solve that. And one of the approaches to solve even the anti-magic labeling for trees was due to Kaplan, Lev, and Roditi. But I need first a definition, and I will show you how they try to solve it. So a K tree is a rooted tree where each vertex, which is not a leaf, has at least K children. Okay, so here this is 2 tree, because every tree, this is my root, right? And every tree which is not a leaf has at least 2 kids, 2 children, right? This has 3, this has 2, this has 2, and this has 3. Okay, so this is 2, 3. So this is some of, let's say, the K-nary trees, right? There are like some special type of these K trees, right? Because here, not that every vertex has exactly the same number of children, but at least children. So, and Kaplan, Lev, and Roditi, they gave this definition. So a gamma star labeling, okay, I have this star of a tree is a bijection from the set of edges to the set gamma minus the identity element. So to non-identity elements such that all the vertex sums are pairwise distinct. Actually, they were working on the case where gamma is a cyclic group, okay? Because if there is such a bijection, right? So we can distinguish, we have this bijection and we have all sums that are pairwise distinct, so we can distinguish all vertices in the group Zn, then actually you can do that in numbers, right? So if this is possible in the cyclic group Zn, right, then what? Then we have an anti-magic labeling of a tree. So they wanted to solve this conjecture. They wanted to solve this conjecture using abelian groups. And I will show you how they used in their proof, because they proved that every K3, if K is at least 2, is possible to do that, how they use the zero-sum subset in groups. So I have this Z11, and this guy has 3 children. This has 2, 2, and 3. And what they did, they wanted to, they partitioned the non-identity element of this group into zero-sum sets of order. I will maybe write it like here. So I have 10 elements in that set, and they partition into zero-sum sets of order 2, 3, 2, 2, and 3. Okay, and this is my zero-sum partition. Okay, and what they did, so look, for the first vertex, so for a root, for the edges adjacent to that vertex, we put the first set. Okay, the labels from the first set. So the root got the weight 0, right?
Mhm.
Okay. And do you see what they did next? For the second vertex, they put the labels from this set, right? So they didn't change the weight of this vertex, right? Because 1 and 10, the set sums to 0, right? So they are not changing the weight of the parent. And we can repeat that, right? And we have the anti-magic labeling. Okay? So that was the idea. That was the idea. And they conjectured that every tree with gamma vertices is gamma star anti-magic, even only if gamma has different number of involutions than 1. And they proved that this assumption is necessary. And actually, when we think about that, then we see that it's really necessary, because if we can make this labeling, okay, if we can make this labeling, then use the we will do the proof by contradiction. So use the double counting. So suppose that we have the labeling, okay, and what will be the sum of the this is the weight, will be the weight of the vertex, the sum of all weights of the vertices in my graph G. It will be the sum of the elements in the group gamma, because all the weights, sorry, it should be gamma here. All the weights are different, right? This is the one side. And the second side is count all edges, right? Now, so each edge is counted twice to that weight. So I have this because I'm using all the elements instead of the identity elements. So what I get will be 0, because from this background from abstract algebra, this sum is either 0 or the involution, right? And if I multiply 0 by 2, it will be 0. If I multiply involution by 2, right, it also will be 0. So if there is exactly one involution, on this hand side, it will be the involution. So I got a contradiction. So then condition is necessary. And they proved together with Zhang that every 2 tree with gamma vertices is gamma star anti-magic, even only if the number of involutions is either 0 or 3 in the group. And me and my friend, based on the theorem about zero sum, we proved that that conjecture holds for every 4 tree, right? For every 4 tree. But the conjecture is false, which I proved this year. And actually, it's false, and it's quite easy to see, because I have here a tree, but it's easy to see for a path. Because suppose that we have the labeling in that group in the path. Okay, so I have the path of, let's say, order 4. So I have 3 edges, and I'm putting here all non-identity elements. So in my group, I have 4 elements. It will be non-identity elements. There are like 1, 0, 0, 1, and 1, 1. You already know. And now it doesn't matter what you put here. There are always involutions, and 2 involutions, they don't sum to 0. So it's impossible that you will get a vertex with a sum 0, and you want to have on vertices all elements of the group. So in particular, you want to have somewhere a vertex, doesn't matter where, which has a label 0, which is impossible. So the conjecture falls. An open problem. So what I did, I defined a gamma anti-magic labeling without a star, and now it will be an injection from the set of edges to the set gamma. So we also allow to have 0. We know that some element of on the edges from the gamma is not used, but not necessarily 0. And we want to have all sums on the vertices different. And I proved that if T is congruent to 2 mod 4, then such labeling doesn't exist for any gamma. And I conjectured that if a tree, this is possible if and only if the tree has different number of vertices than 2, which is not congruent to 2 mod 4. I proved in my paper that this is possible for paths. So for paths, such gamma labeling exists for any gamma that has different number of vertices than 2 mod 4. Maybe I will mention, I don't want to go to definitions, but I know that some of you are working on cordial labeling, right? So this is like edge cordial labeling of trees in a group where group has exactly gamma elements where n elements where n is the number of vertices. So this is like cordial edge labeling. I know that someone of you works on that, so maybe you will have some ideas what to do. Okay. Okay, and now irregular labeling, another types of labeling where we use different approach of zero sums using. But first definition. So an irregular labeling is a mapping from the set of edges to the integers, and now it's not necessary bijection. It's not a bijection, such that what we want to have again, that's why it's anti-magic, such that all the vertex sums are pairwise distinct. Okay, and the idea of this labeling came from multigraphs, because we know that in every graph, simple graph, you have to have at least 2 vertices with the same degree by pigeonhole principle. But in multigraphs, it's not necessarily true, because here the degree of this vertex is 5, here is 4, and here is 3, right? So all vertices, they have different degrees. So instead, drawing multiply edges, you can put numbers, and then you count the weighted degrees, right? And you want to have all weighted degrees have different. And what you are looking for the smallest possible number. And this is the upper bound, which was for a long time the best. So the irregularity strength, this parameter, is, so we are try to minimize it, is at most 6n divided by the minimum degree of the vertex, where n is the order of the graph. And I put here, this is a little bit improved, because here we have the n divided, not 6n by n, but you have here some constants. I don't want to go to details, and this is the newest best result. Okay, encoding of graphs with binary edge labels. So Tuza, I think he was the first one, he was looking to that irregular labeling, but instead of numbers, he used like binary vectors. Okay, binary vectors. So he was in this group Z2 to power m, and he wanted distinguish, right, all vertices. So here is the weighted degrees of the vertices on the group Z2 to the power of 3. And if it's possible in some group, then we say that this graph is realizable in the group Z2 to the power of n. So that was the starting point. And there was conjecture of Agner and Trish that they said that a graph G is realizable in the group Z2 to the power of m if m is in that number. And it was proved by Egava, Pateta, and Gia independently in 2 papers that it's possible if and only if the number of vertices is smaller than 2 to the power of m, but it's not equal to 2 to the power of m minus 2. And I already mentioned that, guys, in the zero-sum sets, right? And it was not by coincidence because the zero-sum sets were used here. But first we will look to the diagraph, to the I have diagrams, but actually they are oriented graphs, because we are in that group Z2 to some power, so it doesn't matter if we add or subtract of some elements, the same, but in the diagrams we can count a weighted degree, like the label that goes to the vertex minus the label that goes out from the vertex, okay? It's like in the networks a little bit, right? And the definition is that if you can distinguish all vertices, right, then the digraph is realizable in the group gamma. So this is quite formal definition. I will show you on example. Okay, here I'm in the group Z5. So what will be the weight of this vertex? 2 goes to the vertex. So here will be 2. 2 goes out, so this is minus 2, but in that group is what? Is 3, right? Because I'm in Z5. Here will be 0 goes 2 and 4 goes 2, so 4 is here, and 1 goes and 0 goes out, so it doesn't matter. And here is 1 and 4 goes out, so this is minus 5, which is 0 in Z5, right? And all vertices are distinct. So this diagraph is realizable in Z5. And note that if you now sum up, don't look to the edges, but just to the vertices. 3 and 2 is 5, which is 0 in Z5. And 0 plus 1 plus 4 is 5, which is 0 in Z5. So each connected component, weakly connected component, has the sum of weighted degrees, which is 0, right? And this is not by coincidence. It has to be like this. So actually, when you have these vertices, you can find the labeling. Here will be 2, here will be 4, here will be 0, and here will be 0, right? And what we can do, we can prove that a directed graph G is realizable in gamma, so we can find this labeling of the arcs, if and only if there exists an injective mapping labeling from the set of vertices such that each component together has some 0 of the vertices. So if you can put the elements of the group in the component such that in each component the sum of the vertices is 0, then you can find the labeling of the edges that you want to. Okay, so what you do actually, you are looking for the partition in the group into zero-sum sets. Okay, so me and George, we prove that simply saying if n is big enough, okay, if n is big enough, then we can, I mean, the order of the group is big enough, then we can find the partition of of this group into maybe not partition, but some zero-sum sets. And I will show you that, because you see that this, if we can find the partition of the group, then we can find the labeling. But this proof, I said that I'm not showing you the proofs of my theorem and Karol Suchan, because they are very algebraic. But this proof, which is for the abstract algebra, it uses graph theory, which I very like. So what is enough? It's enough to show that there exists a partition of gamma into zero-sum sets of order 3, 4, and 5. I is the number, is the set of involutions, and R will be all the set of the remaining elements which are not the identity elements. Okay, so maybe you don't know, but so the involutions and the identity element is isomorphic to Z2 to the power P. And what we will do, we will cover thus many elements bar zero-sum pairs and triples. And I will show you only one case. So the main idea, I don't want to go to the details. We are using, we are constructing 3 uniform hypergraphs such that the edge of this hypergraph, such that the set of this hypergraph, the edge of this is such edge. But each edge, each this A star stands for a power A minus A. Okay? And what is important, that this sum up to 0. So you can think that the hypergraph consists the edges, the hyper edges that are, I will go back to the definition, good set. So 6, 0 good set. Okay? And so this is a good set, as I said. And we will proving using some technical, you have to believe me that each pair of vertices belongs to 0, 1, or 2 hyper edges. And we have each vertex is incident with exactly that number of hyper edges. And then using this information, we are using the corollary by Frank and Rood. And this looks very, maybe not very, but somehow complicated. But theorem of this, the corollary says that if you have a hypergraph, then you can find disjoint hyperedges. So simply saying, you can find, like in a graph, matching, right? Big enough. So we found, using this corollary, matching which is big enough. So what we did, we actually found big enough number of 6 good sets, and this was enough to find zero-sum sets in our group, and we used that to label the graph. Okay, so that was the brief idea of the proof. So proving something in abstract algebra, actually we used hypergraphs and theory of hypergraphs. Okay. So from this corollary follows this theorem, which I already mentioned. Okay, that if n is sufficiently large, then we can find the irregular labeling of directed graph in the group gamma. Okay, we also proved this theorem, so that we can find the irregular labeling in gamma if gamma is at least 2n plus 2 square root of n, and it was by greedy algorithm, but we were able to do that. And using the result of me and Karol, if gamma has not unique evolution, then we, in any group which has at least n plus 5 elements, we could find this irregular labeling. And recently, I improved that for any gamma, but gamma has to have at least n plus 6 elements. Okay, how much time I'm left with?
I think 5 minutes.
Okay, so I will now jump to some other slides.
But I think it can be until 10 also.
Okay, so maybe I won't. So for notes graph, we also considered the group irregularity strength. So now we are just summing labels. And you want to label a graph in any group of order n. So this is a labeling of C4 in the groups Z4 and Z2 times Z2. And now if you count the sum in each vertex of the adjacent edges, right? Like here, this is in group Z4, this is in group Z2 times Z2. All the weighted degrees are different, right? So we are able to do that. So the irregularity strength is 4. So this is the lowest S such that for every abelian group of order S, there exists a gamma irregular labeling of G. So you know that graph probably, and this graph has 10 vertices. And one could think that you can do this labeling in Z10, but it's impossible, which shows this theorem. So the irregularity strength, we found the exact number is n plus 2 for some very specific graph, is n plus 1 when n is congruent to 2 mod 4, and G is not this very specific graph, and n is otherwise, right? So n is the lower bound because we want to distinguish all vertices, right? So the group has to have at least order n. And this is important that this is for connected graph. For not connected graph, we couldn't find anything better. We only found some upper bound, which is 2n. And recently with my PhD student, we could improve this upper bound for a graph which doesn't have like small stars as components. So this, you can do that for sure in any group which is at least of order n plus 7. Okay, so the idea of the proof, because I told you that I will use this zero sum. So we use the set of alternating paths. So we partition the set of vertices into pairs and triples, and we find zero sum partition of the group such that this partition, each element has set has vi elements, and for each set we construct a set of alternating paths. Because if I have such a path, so I put a minus a minus a, then these middle vertices, they have 0, right, label, and these ends points, they have different a minus a. And we sometimes use triples, and here you have the triple ABC, they sum to 0, and we use such constructional paths. So that's why we needed this zero sum sets. So this is your graph. And I said that Z10 is not enough by the theorem. So I will show you that Z11 is enough to label this graph. So I will use the partition like 1 and 10, 2 and 9, 3 and 8, 4 and 7, and 5 and 6. So these colors, I join the vertices into pairs, okay? So I have this alternating path. So here I will put 1 and 10 for that maybe I'll use different color for that path. So this vertex got the weight 1, and this got the weight 10, right? For that path, red and red, I will put 2 and 8. So the vertex 1 red got the weight at degree 2, and the second got the weight at degree 8. Okay, so I'm using this system, and I can distinguish all vertices in that graph. Okay. And open problems is that we believe that for any gamma, which is at least n, where n is the number of the vertices in directed graph plus some constant k, you can do that, and we have the same conjecture for a graph which is not directed, and the conjectures are open, which is important that here we have at least 3, and the best results are here is 4. Okay, and the last one. That's why I wanted to jump, because I know that some of you works on distance magic labeling. So the last application on that kind. So maybe I will say very fast about the definition because most of you know this definition very well. So distance magic labeling of a graph G. In this is the first labeling today. When you label the vertices, this is a bijection from 1 up to n, such that when you count the sum of the adjacent of the neighbors of each vertex is the same. It's magic constant. Okay. So here are labeled the cycle C4, and you see that each vertex has the neighbors with the sum 5. And I have here two observations. First is I think also to Rino, it's also your paper, right, with Mirka?
Yes.
Yes. So first we have what is the sum in R regular graph, what is the magic constant, and the second from the first follows that if R is odd, then no R regular graph can be distance magic graph. And that was in numbers, and similarly for groups. So instead of numbers, we're using groups elements. We label the graph, the vertices. So here I have Z5 distance magic labeling of the graph G, because if you count the sums of neighbors, it will be 0 in the group Z5, right? So it's constant. And with Dalibor, we proved that if R is odd again, then you cannot find such labeling in any group that has exactly one involution. And I need this. This is a lexicographic product of the two graphs. This is like P3 blow up into complement of K3. What we do actually, we blow each vertex of P3 into that graph, right? So I got the result. So you can think that K and maybe N, where it's T, it's like PT, which is blown to Kn, the complement of Kn. Sorry, not PT, but CT, KT. Now it's correct? Yes, now it's correct. Sorry. Here I have this. And so I would like to label this graph. So what I do, actually, I have like 4 sets of order 3, and I would like to do that in the group gamma, which has 12 vertices, and I can do that unless the group has one involution, because I will find a partition in that group into 0 sets of size 3. So if this set has size 3, this set has size, or sums 3, and this also has some 0, then I will put the elements of those sets on the vertices, and then each vertex will have the magic constant 0. Okay. And open problem here, the last one. My question is, does there exist an odd regular Z2 to the power m distance magic graph G? And it's not, I was thinking a little bit about that, and I couldn't find any example of odd regular graph which is Z2 to the power of m distance magic graph. Maybe some of you will be able to do that. I can only say, but I don't have time to explain why. If R is 3, there does not exist. That graph. So you have to think R needs to be at least 5, this regularity. Okay, and that's it. Thank you very much for the attention.
Okay, thank you, Sylwia, for a very interesting talk. So I think we will move to the question and answer session. But before that, do you have something, Paide, or should we first?
I have some music for
Okay.
Sylwia.
So music first before question. Okay.
Okay.
So probably, can you close your slide, Sylwia?
Yes. I'm doing that. Wait a second. Wait a
Yes.
second. Yes, I stopped.
Okay. Okay, please, Pak Edi.
Okay. Now, okay, we will hear some music first. This is actually from Rino's album. So
Wow.
yes, Rino has make many songs, album songs. Yeah. So this is Over the Rainbow from Eduns, from Rino's
Wow.
band. Yeah. Terdengar suaranya Rino?
Terdengar, Pak.
I don't hear.
Now it's gone. I think the sound is gone now, Pak Edi.
Yes. I don't hear.
Kelihatannya timbul hilang ya Pak suaranya.
Huh?
Ini hilang lagi. Mungkin diulang aja Pak, dimatikan dulu. Okay, sorry for the technical problem.
I need to find it in. Is it on YouTube?
Yes,
It's
and
on YouTube, yes.
so
Okay, so I need to find it. I didn't. I need to find the band. I didn't know that you sing in the band.
okay, just
So
the promotion, the
you have to
promotion
send
of
me the band.
okay, back to Rino. Rino.
Okay, so we go to the question and answer, Pak Edi.
Yeah.
Okay, sorry about that. Probably there is some technical problem with the sound. Okay, we already have 2 questions in the chat box. First is from Roslan Hasni, I'm sorry. So he asks, hello Sylwia, group irregularity strength is interesting. Are there more open problems to explore? So maybe you can answer that one first.
Yes. There are something called. It was defined by Ping Zhang, right? Ping Zhang.
Yeah.
I think she worked with some of her PhD students, which is called modularity strength or something like this. So we considered all abelian groups, and what they did, they considered only the cyclic groups. And also for cyclic groups, okay, the result of course follows from ours, because we considered all groups. But maybe you can make something better because you have only one group, right? A cyclic group, right? Like one in quotation, because of course you have a lot of them. So I think that you can look to the cyclic groups.
Okay. Okay, the second question is from William. So we have M and B in abelian group G. Would the structure be similar if the vertex sum of the digraph is changed in M multiply by W if in? So I think it's the direction of the the R pivot, yeah, okay, and times W if out, with W is the weight of H.
Interesting question, and I think yes, because what we used here, that like this M and N was 1, right? And that's why the sum was 0. So yes, it changed a lot, but I don't know how much. But it changed a lot, yes.
Yeah. Do you know anybody who already work in this, or?
No.
This is something
no,
new,
I didn't see such modification.
All right.
But yes, it's interesting.
Okay. Okay, so the third question is from Muhammad Rafi Fajri. So in the group distance magic labeling, the example is Z5 distance magic labeling of G. How can we determine the labels for each vertex to satisfy the group magic constant condition? I don't really understand the question. So probably Muhammad Rafif, can you ask or give more explanation about the question? Muhammad Rafif, are you still here, or?
He's on the road, I think.
Oh, he's on the road. Okay, so I don't know. Maybe Sylwia can give interpretation about the question.
I don't know. Maybe the interpretation is, I don't know, that the magic constant is fixed. So the question is like for when you have the distance magic labeling in numbers, then we know by very nice results. There were for sure Armugan and one paper, which has very beautiful proof using algebra, right? And the second one was using domination number somehow, right? And the magic constant is unique in numbers, what I wanted to say. But in group is not necessary, right? So so it can happen that you can, this is the question, that you want to have that the magic constant is some element, but it's impossible to obtain any labeling. So maybe it was the question, if you have the group magic constant that is given, can you find the labeling? Not always, right? Not always. But I don't know. Like when you have I can say that in that my open question for this R regular graphs where R is odd, we can assume that the magic constant is 0 without loss of generality.
No,
without loss of generality. Yes, because if there exists some other, right, you can simply transform the labeling to such labeling that has 0 magic constant by adding something on the edges. So we can assume that the magic constant is 0, and that's because of this. We know that free regular graphs, they don't have this magic labeling when we think about that a little bit more. Yeah, but I think that it was because Rina and me, we have some paper on cube on hypercube, right? Hypercubes, and we know that if the degree of hypercubes is odd, then we cannot find such labeling, right? In our paper, we have like if and only if the result. So the question is, what about other graphs? It's not so easy answer. There are some odd regular graphs that they have distance magic labeling in group distance magic labeling. But this is not a group Z2 to some power m, like in because in hypercubes you have only that groups, right? And like in this example, like K3, 3, 3, 3, the group has order 12, right? And we know that a group that has more than one evolution, this is like Z2 times Z2 times Z3, and you can find this labeling by zero-sum partition, right? But I couldn't find any graph of order this 2 to power m, which has odd regularity, and group distance magic labeling in this Z2 to power m. So this is the question.
Mhm.
It's important that this is this group.
Yeah.
Okay.
Okay. Okay. Okay, so Rafif is outside, so he couldn't turn on the mic. Okay. But hopefully it give an answer to your question. Okay, thank you, Pak Roslan, William, Muhammad Rafif. Is there any other question?
Can I have one?
Okay, please, Pak Edi.
Okay. So, do you have any application to the group total irregular strength? So you
Group
mentioned,
total.
yeah, total irregular strength. So the
So
vertices you also label, not only
Label
yes.
vertices and
Yes.
edges and
No, I
calculate
don't.
in vertex, yeah?
No, I
for
don't have.
using the group, the
I have
zero sum group, zero sum set. No?
no. I don't have. I have some something when you label the vertices and you want to distinguish edges, but I don't have like total. So no, 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 no.
And what about the application of zero sum sets into natural magic and anti-magic labeling without group? Is it possible to apply that if you have zero sum sets and then you apply to get magic labelings or anti-magic labelings?
I don't see, because in that group when Kaplan, Leff, and Roditi they were they use this cyclic group ZN, and then you know, instead of 0 you put the label n, and since everything is different modulo n, it's different like in numbers, right? But this is like very, you know, there are very strict sets, right? You have the elements. I don't know what about like arbitrarily set which are zero sum. I'm sorry, no, don't know.
Okay.
I think that in regular graphs maybe it would be useful in regular graphs, right? Because you can shift the labels maybe somehow.
Yeah.
And then you add like the same sum to every vertex, but in non-regular graphs I don't see.
Okay, then thank you, Sylwia.
Thank you.
Yeah.
Okay, is there any other question? Maybe one more question, if there is one. Okay, if there is no other question, thank you for everyone who already asked question to Sylwia, and also let's thank Sylwia again for a very interesting talk.
Thank you very much.
And I will give back the screen to Pak Edi.
Okay, so again, so we thanks to Sylwia for nice and interesting talk today, and we would like to give you a certificate, and here I will show you the certificate, and we will send you later through the email.
Okay.
Let me show you. Okay, so this is the certificates from our department.
Wow, nice.
Yeah, so again, this award is presented to Professor Dr. Sylwia Cichacz for sharing her valuable knowledge as a keynote speaker in the Combinatorics Today series. And also, I give you another one, which is with your photo. Yeah.
Wow, nice. Thank you. Thank you.
I hope.
I'm really honored and really happy.
Okay, so I hope I mean, you enjoy this certificate, and also you enjoy giving lectures in this event. So
Yes,
again,
I enjoyed
we
a
are
lot.
very thankful for your lectures today, and actually, we would like to invite you to come to Bandung, yeah, next time,
Ah,
yeah. Yeah, so we should arrange some conference, you know.
yeah.
Yeah. We should have some conference, and Sylwia should give keynote talks in this
I
conference.
will go by the
A Woggle, yeah, next
Indonesia.
year. Next year we will have a Woggle. Okay. We'll be in Indonesia. Yeah.
Ada Andrea juga nih.
And also Andrea. Yeah, okay.
Oh, Andrea is here.
Okay, so again, thank you, Sylwia.
Thank you.
Thank
I'm
you,
very
everybody,
happy. It was great
to
pleasure.
be in this event. Hopefully, next month or next 2 months, we will meet again in this event, Combinatorics.
Okay. Eddie, I would be very, very happy if you add me to the mailing list. Sometimes I'm teaching, so I don't have time. But if I don't teach, I would. On Monday I'm teaching, but maybe some other time I could join you because I would like to. So can you add me to the mailing list
Yes.
Sure.
to
Yeah.
send me the information about the seminar? Okay. Thank you very much. It was great pleasure to
Thank
see
you,
you.
Sylwia.
Thank you. Thank you very much. Yeah.
Thank you, everybody, for coming.
Sylwia.
Everybody, so see you next
Thank
time.
you, Pak
Yeah,
Samin,
bye-bye.
Bu
Pak
Kiki.
Samin. Andrea, thank you.
Thank you, Andrea.
Andrea,
Okay.
bye.
Bu Denny, ya, oke. Ya, bye-bye.
Bye.
Bye.
Semua.